Integration of powers and products of secant and tangent, and cosecant and cotangent. Powers of secant and tangent. The general problem we want to consider here is the indefinite integration of a power of secant times a power of tangent. It's worth pointing out that integrands of this sort can also be written in the form of a power of sine divided by a power of cosine, where the power of cosine in the denominator is at least as large as the power of sine in the numerator. Now let's look at the simplest cases here. There are two that we're already familiar with. The integral of secant squared x dx equals tangent x plus c, since secant squared is the derivative of tangent, and the integral of secant x tangent x dx equals secant x plus c, since the derivative of secant x is secant x tangent x. What about the integral of tangent x dx? By writing tangent as sine x over cosine x, and then making the substitution of u equals cosine x and du equals minus sine x dx, this becomes minus the integral of du over u. So we have minus the natural log of the absolute value of u plus c, where u equals cosine x. In other words, we have minus the natural log of the absolute value of cosine x plus c. Now we can absorb the minus sign here by replacing cosine x with its reciprocal, which is secant x. So the indefinite integral of tangent x dx is the natural log of the absolute value of secant x plus c. Now what about the integral of secant x dx? Well, to get from here to there, we need a very special trick. What we're going to do is multiply secant x by secant x plus tangent x divided by itself. Now when we multiply out the numerator here, we have secant squared x plus secant x tangent x, which turns out to be exactly the derivative of the denominator. So if we substitute u equals secant x plus tangent x, this becomes the integral of du over u, and so we have the natural log of the absolute value of u, where u is secant x plus tangent x. So the indefinite integral of secant x dx is the natural log of the absolute value of secant x plus tangent x plus c. Since we've covered secant squared, what about tangent squared? The key here is to use the trigonometric identity that's derived from the Pythagorean identity, sine squared x plus cosine squared x equals 1, by dividing through by cosine squared x, which gives us tangent squared x plus 1 equals secant squared x, which tells us that tangent squared x is the same thing as secant squared x minus 1. So let's rewrite the integrand there as secant squared x minus 1, and now we've got two terms that we can integrate. Secant squared x gives us tangent x, and minus 1 gives us minus x, and we add our plus c. Now in the case of the integrals of the first powers of tangent x and secant x, we recommend that you remember those results. The way the integral of tangent x is obtained is very straightforward, but the way that we found the integral of secant x is a very special trick that's as hard to remember as the result is, so we may as well just remember the result. Here's an example that's typical of the case where we have an even power of secant. Let's consider the integral of tangent squared x times secant to the fourth x dx. The key here is to factor secant to the fourth x into secant squared x times secant squared x and group one of those secant squared x's with dx, so that we can think of that as du with the idea of substituting u equals tangent x. Now in order to make that substitution, we need to express the remainder of the integral in terms of tangent. In particular, we need to rewrite the other secant squared x in terms of tangent. So we replace secant squared x with 1 plus tangent squared x. Now we're ready to make our substitution. We replace tangent x with u and replace secant squared x dx with du, and we have the integral of u squared times 1 plus u squared du. Now to do the integration, let's multiply out the integrand. It's the integral of u squared plus u to the fourth times du. So we have 1/3 u cubed plus 1/5 u to the fifth plus c. Now before we substitute back, let's factor out a 1/15 times u cubed. The other factor then is 5 plus 3u squared. Now finally we replace u with tangent x. Now this example is typical of how this kind of problem can be handled anytime we have an even power of secant. This is what the general case looks like. Suppose we have some power of tangent and an even power of secant. Since we have an even power of secant, we can pull off a secant squared x to group with dx, thinking of that as du, where we intend to make the substitution of u equals tangent x. So we then have to express the other secant factor in terms of tangent. We do this by replacing secant squared with 1 plus tangent squared. Then we make the substitution u equals tangent x, and we have the integral of a polynomial, whose integration is in principle an easy thing to do. Now let's look at an example that's typical of the case where we have an odd power of tangent. Let's consider the integral of tangent cubed x times secant cubed x dx. Here we can take a factor of tangent x times secant x together with dx and think of that as our du, where we hope to substitute u equals secant x. Now notice that since the power of tangent was odd, taking secant times tangent away left us with an even power of tangent, which makes it easy to express that in terms of secant. In this case, we need to express tangent squared x in terms of secant. That's easy to do. Tangent squared x is secant squared x minus 1. So now we're ready to make the substitution. We replace secant x with u, and secant x tangent x dx with du. Then multiply out the integrand. We have the integral of u to the fourth minus u squared du. Integration gives us 1/5 u to the fifth minus 1/3 u cubed plus c. Now let's factor 1/15 u cubed. The other factor is then 3u squared minus 5. And now we replace u with secant x. Now let's think about the general case where we have an odd power of tangent and at least one factor of secant. Then we can group a factor of secant x tangent x with dx. Think of that as du. Then we replace tangent squared with secant squared x minus 1. Replace secant x with u and secant x tangent x dx with du, and we have the integral of a polynomial. We then integrate that polynomial and replace u with secant x. Now let's look at an example where the secant factor is missing. Let's consider the fifth power of tangent x dx. Let's take tangent to the fifth x and factor that into tangent cubed x times tangent squared x. Then we'll rewrite tangent squared x as secant squared x minus 1. Now when we multiply that out, we have tangent cubed x times secant squared x, which is already easy to integrate because secant squared x is the derivative of tangent squared x, and we can use a simple substitution there. The other term, minus tangent cubed x, has a lower power than we started with. In fact, we can repeat what we've just done on that term. We'll write tangent cubed as tangent x times tangent squared, and again replace tangent squared with secant squared x minus 1. Now let's multiply that out, and then factor secant squared x from the first two terms, and we have tangent cubed x minus tangent all times secant squared x plus tangent x. So the integral of tangent to the fifth x dx is equal to the integral of tangent cubed x minus tangent x times secant squared x dx plus the integral of tangent x dx. The first integral there is already set up for the substitution of u equals tangent x. It becomes the integral of u cubed minus u times du. When we integrate u cubed minus u, we get 1/4 u to the fourth minus 1/2 u squared, or 1/4 tangent to the fourth x minus 1/2 tangent squared x. And then the second term, the integral of tangent x dx, we'll recall, gives us natural log of absolute value of secant x plus c. The method that we used on the previous example can be represented nicely as a reduction formula for powers of tangent. So let's consider the indefinite integral of the nth power of tangent x dx, where n is a positive integer. We'll rewrite the nth power of tangent x as the n minus 2 power of tangent x times tangent squared, where we replace tangent squared x with secant squared x minus 1. Then we multiply out the integrand and break it into two integrals. First, the integral of the n minus 2 power of tangent x times secant squared x dx, and then minus the integral of the n minus 2 power of tangent x dx. Now the first integral is easy to compute. We substitute u equals tangent x and du equals secant squared x dx, and so we integrate u to the n minus 2 power du, which gives us u to the n minus 1 divided by n minus 1. So that term becomes 1 over n minus 1 times the n minus first power of tangent x. So we have that the integral of the nth power of tangent x dx is 1 over n minus 1 times the n minus first power of tangent x minus the integral of the n minus 2 power of tangent x dx. And this is a formula that's valid as long as n is an integer that's greater than 1. So this is a reduction formula that's derived based simply upon a trigonometric identity as opposed to integration by parts. So now let's look at an example. Let's compute the integral of the 6th power of tangent x dx. We first apply the formula with n equals 6. We get 1/5 of the 5th power of tangent x minus the integral of tangent to the 4th x dx. Next, we apply the same formula to the integral of tangent to the 4th. Using n equals 4, that becomes 1/3 tangent cubed x minus the integral of tangent squared x dx. Now we apply the formula once more. Using n equals 2, we write that as tangent x minus the integral of the 0th power of tangent x, or the integral of just dx. Now, of course, the integral of dx is x plus c, and now we'll remove the parentheses and write this as 1/5 tangent to the 5th x minus 1/3 tangent cubed x plus tangent x minus x plus c. So now we come to what is maybe the most interesting case, that is, odd powers of secant. Odd powers of secant need to be handled by power reduction via integration by parts. Now let's look at the example of the integral of secant cubed x dx. We'll do this by parts as follows. We'll let u equal secant x, so that dv is secant squared x dx. Then du is secant x times tangent x dx, and v is equal to tangent x. Now we have u times v being secant x times tangent x, and now we subtract the integral of v du, and v times du is secant x times tangent squared x dx. Now we rewrite tangent squared as secant squared minus 1, multiply out the integrand there, and break the integral into two parts. So now we notice that the integral of secant cubed appears on both sides of this equation. It has a minus sign in front of it on the right, so let's add the integral of secant cubed x dx to both sides and get 2 times the integral of secant cubed x dx on the left, and secant x tangent x plus the integral of secant x dx on the right. Now we divide by 2, and we have the integral of secant cubed x dx expressed in terms of the integral of secant x dx. Now we're going to factor off a half and recall that the integral of secant x dx is the natural log of the absolute value of secant x plus tangent x. So we now have the integral of secant cubed x dx. So now let's consider the general reduction step. Say we have the integral of the nth power of secant x dx, where that power is at least 3. We approach this by parts by setting u equal to the n minus 2 power of secant x and dv equal to secant squared x dx. Now we compute du, and we get n minus 2 times the n minus 3 power of secant x times secant x times tangent x dx by the chain rule. Now let's combine those two secant factors into the n minus 2 power of secant x. Now we integrate secant squared x dx to get v equal to tangent x. So now we write u times v, the n minus 2 power of secant x times tangent x, minus the integral of v du, which is minus n minus 2 times the integral of the n minus 2 power of secant x times tangent squared x dx. Now we replace tangent squared x with secant squared x minus 1, multiply out the integrand, and break the integral into two pieces. So now we notice that we've got a multiple of the integral of the nth power of secant x on the right side, so we'll add n minus 2 times that integral to both sides, Now n minus 2 plus 1 is n minus 1, so we have n minus 1 times the integral of the nth power of secant x dx on the left, and on the right we have the n minus 2 power of secant x times tangent x, plus n minus 2 times the integral of the n minus 2 power of secant x dx. Now we divide by n minus 1, and we have our reduction formula. We emphasize that what this formula is really about is a description of what happens when you do one step of integration by parts on a power of secant x. Also, we could apply the formula here for any n greater than or equal to 2. However, it's most useful when n is odd. When n is even, there are better ways of doing things, as we've already seen. Now let's look at a couple of examples. Even though we've already computed it from scratch, let's use this on the integral of secant cubed x dx. With n equals 3, the coefficient in the first term is 1/2, and the power on secant is n minus 2 equals 1, so we have 1/2 of secant x times tangent x plus 1 over 2 times the integral of the first power of secant x dx. Now we factor a 1/2 and recall that the integral of secant x dx is the natural log of the absolute value of secant x plus tangent x. Now let's find the integral of the fifth power of secant x dx. Using the formula here with n equals 5, we have 1/4 of secant cubed x times tangent x plus 3/4 the integral of secant cubed x dx. Now we've just computed the integral of secant cubed x dx, so let's use that here and write 1/4 of secant cubed x tangent x plus 3/8 secant x tangent x plus the natural log of the absolute value of secant x plus tangent x plus c. Now let's clean this up a little bit by factoring out 1/8 and then noticing that the first two terms share the common factor secant x times tangent x. So let's write 2 times secant squared x plus 3 times secant x tangent x plus 3 times the natural log of the absolute value of secant x plus tangent x plus c. Now there's one final case to consider. Here's an example of an odd power of secant together with an even power of tangent. The indefinite integral of secant cubed x times tangent squared x dx. The way to approach this is to basically convert to odd powers of secant only. If we replace tangent squared x with secant squared x minus 1 and then multiply out the integrand, we can break the integral into two parts, the integral of secant to the fifth x dx minus the integral of secant cubed x dx. Now we just computed each of those on the previous page and we could use the results here, but let's go ahead and work this out. We'll use our power reduction formula. First on the integral of secant to the fifth. There we get a 1/4 tangent x times secant cubed x plus 3/4 of the integral of secant cubed x dx. Then we have our second term minus the integral of secant cubed x dx. So notice now that we can combine those two terms and write this as 1/4 of tangent x times secant cubed x minus 1/4 of the integral of secant cubed x dx. Now we apply our reduction formula with n equal to 3. Notice that in that case, 1 over n minus 1 and n minus 2 over n minus 1 are both equal to 1/2. So we can factor a 1/2 from the two terms, and we have minus 1/8 of secant x times tangent x plus the integral of secant x dx, which we recall is the natural log of the absolute value of secant x plus tangent x. Now let's factor out a 1/8 and remove the parentheses. So now let's summarize what we've learned about integration of a power of secant times a power of tangent. If we have an odd power of tangent, and the power on the secant is at least 1, we group secant x tangent x together with dx, thinking of that as du for the substitution u equals secant x. This requires us to express everything except secant x tangent x dx in terms of secant x. We do that using the identity tangent squared x equals secant squared x minus 1. If we have an even power of secant, then we group a factor of secant squared x with dx and think of that as du for the substitution of u equals tangent x. This requires us to express everything in the integrand except the secant squared x dx in terms of tangent, which we do by means of the formula secant squared x equals tangent squared x plus 1. If the secant factor is missing, then we reduce powers by replacing a factor of tangent squared with secant squared x minus 1. We then expand that product and break the integral up into two. If we have an even power of tangent with an odd power of secant, then we express with odd powers of secant only and then reduce powers with integration by parts, or a reduction formula that encapsulates one step of parts. We want to remember each of the following integrals. The integral of secant squared x dx is tangent x plus c. The integral of secant x times tangent x dx is equal to secant x plus c. The integral of tangent x dx equals the natural log of the absolute value of secant x plus c, and the integral of secant x dx equals the natural log of the absolute value of secant x plus tangent x plus c. Cosecant and cotangent. It turns out that the integral of a power of cosecant x times a power of cotangent x dx can be handled in a manner that's completely parallel to how we handle the analogous integral involving secant and tangent. So we'll just summarize these parallel techniques. If we have an odd power of cotangent and at least one factor of cosecant, we can put a cosecant x times cotangent x together with dx and make the substitution u equals cosecant x. If we have an even power of cosecant, then we can group a factor of cosecant squared with dx and make the substitution u equals cotangent x after expressing the remainder of the integral in terms of cotangent. If the cosecant factor is missing, then we reduce powers by replacing a factor of cotangent squared x with cosecant squared x minus 1. If we have an even power of cotangent with an odd power of cosecant, then we express with odd powers of cosecant only and then reduce powers with integration by parts, or a reduction formula version of that. Now we want to remember these integrals. The integral of cosecant squared x dx is equal to minus cotangent x plus c. The integral of cosecant x times cotangent x dx equals minus cosecant x plus c. The integral of cosecant x dx equals the natural log of the absolute value of cosecant x minus cotangent x plus c. And finally, the integral of cotangent x dx is equal to the natural log of the absolute value of sine x plus c. And this can also be written as minus the natural log of the absolute value of cosecant x plus c.